a couple of ideas. Well, okay. First question I have for you guys is, you guys did the reading. Looking at time, is there anything that you want me to go over? Let me ask that. Okay. So, we showed on today's quiz that multiplying a vector in Rn by an m by n matrix, maybe I should say left multiplication, right? Because you put the matrix on the left. Left multiplication of a vector in Rn by an m by n matrix is a linear transformation. So we showed that. And then what I've been trying to get at is this. What is really cool is that every linear transformation you can think of, any map that follows those two rules, every linear transformation can be described in this way. What way? Well, as a matrix. So basically, that's the point of theorem 3.31 in your book. And when you say the standard matrix, Mitchell, that's what they're talking about. Okay? So let me actually kind of work through that theorem for you. I think that's important. Okay? So theorem 3.31 says the following. It says, let T, which is a map from Rn to Rm, suppose that's a linear transformation. Okay. Then T is a matrix transformation. More specifically, T equals TA, where A is the matrix maybe I should even say m by n matrix. M by n matrix, here it is. A is, the first row is TE1. The second row is, these are columns, I'm sorry. The second column is TE2, dot, dot, dot. And the last column, how many columns are there? N. So the last column would be TEN. And just to kind of remind you guys, do you know what I mean again when I say E1 or E2? Do you guys know what these vectors mean? What is it?
Identity column.
Yeah, it's kind of like an identity column would be one way of saying it. It's a unit vector, right, with a 1 and the rest zeros. And basically, the 1 shows up wherever the number is. So E2 is going to be 0, 1, and then all zeros below that. By the way, E1, E2, ... En is known as the standard blank for Rn. Do you know what I'm going to put in the blank? Basis, that's right. It's the standard basis because they span Rn. Any Rn is a linear combination of these. And they're obviously linearly independent too, because when you put them in a matrix, they're going to be rank n. Okay? So again, the take-home message for today is this. If you want to understand a linear transformation, look at what it does to a basis. That's really kind of the take-home message today. If you want to understand what a linear transformation does, look at what it does to the basis. Oh, and then just to kind of address what you asked, Mitchell, this thing here, this matrix, this is called the standard matrix of the linear transformation T. So that's the standard matrix of the linear transformation T. So let's see. A linear transformation from R3 to R2, and I want to give you an example of a nonlinear transformation from R3 to R2. So the linear transformation, I'm going to say this. T here is going to be, well, T of what? I need to give you something in R3. So how about I say X, Y, Z. T of X, Y, Z equals, and now I need to give you something in R2, right? So the first coordinate, let's make it X plus Y, and let's make the second coordinate Y plus Z. Okay? It turns out that that is a linear transformation. Okay? And you could check the two rules. That'd be a good test exercise. Hey, check that this is a linear transformation. This one is a nonlinear transformation. I like this example. T of X, Y, Z equals, and so suppose you take X times Y and make that the first coordinate, and you take Y times Z and make that the second coordinate. That's not a linear transformation. Is it a transformation? Sure. It changes, right? It takes anything in R3 and it'll spit out something in R2. Right? By the way, one thing about this transformation, graphically, I was just thinking about this. You know, if I were to draw all of R3 here, here's X, here's Y, and here's Z, and I look at what this I'll call this one S. T is going to be the good one. And if I look at what S does to it, it maps it to the XY plane, right? Here's something that I think is kind of cool. Which points from here, from R3, would get mapped to the origin, 0, 0? Can you tell me? if you want the output to be 0, 0, I guess what I need is I need x times y to equal 0, and I need what else to be true? Y times z to equal 0, right? So when would that happen?
On the xc plane, whenever y is equal to 0.
If y is equal to 0, then, right? So that means this entire plane, the xz plane, somehow gets mapped to that single point. This is not what's called a linear transformation, okay? Now you can have linear you're going to have similar kinds of things here. You're going to have, again, a space R3 getting mapped to R2, but it's a little bit different, okay? So the geometry is not what I want to focus on today, although it's very interesting to think about. When you're doing your homework, you might want to draw drawings like this sometimes. But what I want to focus on is how do we express the matrix that represents what's going on here. First of all, I'm going to call it matrix A. What size should matrix A be? Let's get that down first. Well, we're going from R3 to R2, so what size matrix do I need? Almost?
1 by 2.
No. 2 by 3. Rn to Rm, right? So 2 by 3 is what I need. So I'm going to create a 2 by 3 matrix here, right? It has 2 rows and it's going to have 3 columns. Is this okay? What are the 3 columns supposed to be? Well, the first column is supposed to be T of E1, right? This column is supposed to be T of E2, and this column is supposed to be T of E3. And I guess I have to work those things out a little bit. Now, when I say T of E1, what I really mean is T of 1, 0, 0, right? And that is what vector? Well, I guess it's 1 plus 0 and 0 plus 0. So this is the matrix 1, 0. That's the first column of my matrix. Does that make sense to you guys? Let's see if you can figure out the other parts. T of E2, we're going to do T of what? 0, 1, 0. And again, if you follow the rule, x plus y and y plus z, it's not hard to see that this is going to be 1, 1. Does that make sense to you guys? 0 plus 1 and 1 plus 0. How about T of E3? That's T of 0, 0, 1. What's that going to be in this example? Uh-oh. You guys have it or no?
0, 1.
0, 1. Okay. So, that matrix does the exact same thing as my linear transformation. Let's check that, you know? Here. Give me a point somewhere in R3. 1, 2, 3. How about that? Okay? If I wanted to compute T of 1, 2, 3, let's go back up here, and just use the rule, you could do that. What would it equal? I guess it would equal 3, 5. Is that right? 1 plus 2 and 2 plus 3. Okay? Now I want to do it using my matrix A. So what I do is I take matrix A and I multiply my matrix by 1, 2, 3. And you could check that that's going to give you 3, 5. How do I see that? I don't know. Depends how you want to do the matrix multiplication. There's a lot of ways to do it. Maybe what I'll do is call it 1 times 1, 0, right? Plus 2 times 1, 1 plus 3 times 0, 1. Do you see it works? Yeah, it really does give me 1 plus 2 is 3, and then 2 plus 3 is 5. It gives me what I wanted. So again, if you want to know what does a linear transformation do to a set of vectors, look at what it does to a basis. Especially if you have a subspace, you'll have a basis, and then you'll know what it does. That's really cool. So why do you guys have to study linear transformations? Part of it is, I mean, you guys are here, some of you, because you're going into computing, and a lot of transformations are carried out, are done by linear transformations. I'm just going to show you a little picture here of some transformations of the Mona Lisa. I thought this was kind of cool. It's something I can show you quickly. And what we have here are we have the matrices that correspond to doing different things to the Mona Lisa, right? Well, of course, what's this matrix? So it didn't change the Mona Lisa at all, right? What did this matrix do? That's a rotation matrix, you could say. We rotate it by 90 degrees, okay? What's this matrix doing? It's stretching, multiplying the x direction by 2, but the y direction is not being changed. And so, see what it does? Kind of stretches her out. What's this matrix do? Of course, if you rotate 360, a flip, that's right. So the x coordinates we took the opposite of it, right? And so we take the Mona Lisa and so just in the world of graphics, right, computer graphics, you could see where a knowledge and understanding of linear transformations is a good idea. But one of the things I like is your book has a pretty cool example also where they talk about robotic arms. And so you're in 3 space and you want to move these things. How? Rotations. Most of the movements you'd want to make can be described by linear transformations. And the fact that we can compose linear transformations and put them together by multiplying the matrices together allows for very complex movements of these things. So I know I'm only skimming the surface. You could take a whole class if you're an engineer on transformations, and you may, some of you, okay? But at least it's kind of nice to know where their origins are. All a linear transformation is multiplication by a matrix.
So with those transformations, wouldn't the transformation matrix have to have as many columns as the picture had pixels and width?
No. So let me think for a
I
minute.
might have gotten that wrong.
The reason it doesn't need that is because what we're doing is I'm saying that every single point on here has an x and a y coordinate. Okay? And so when I create this one, how did I do it? I take x, y, and I multiply by that matrix. And so it's going to take what was this corner point and it's going to send it up here. Let me check that. If this were the point, I don't know, 15 comma 0, and if I multiply 15 comma 0 by that, where does it go? Well, it's 15 of the first vector, so it goes to 15 down here, and it's 0 of the second, so it goes to, oh no, it's negative 15 here, right? Wait, did I do that right? Hold on. I'm losing it. Let me try again, and then I'll come back to the picture. If we take 0, negative 1, 1, 0, and multiply by 15, 0, because that's what I said the bottom right corner was, let's pretend. What do I get? So the first coordinate I get is 0, right? Because it's 0 times 15, negative 1 times 0. The second row I get is 15. Okay, so, this may be a typo. Because it looks to me like if 15, 0 gets sent to 0, 15, oh, I see. The axes are here in the second picture. So it took the whole picture and flipped it around the axis and ended up in quadrant 2. This is quadrant 1 initially. Does that make sense? So that would be a way of representing it. The only other thing you could do is if you put the origin right in the middle, it'll work out perfectly, just as a rotation only. Okay. Any other questions before we take our break and get ready for presentations? Okay. Well, I think you have enough to work on the homework over the weekend.